Hi everybody, very glad to see you here. In this session, I would like to try to introduce some basic knowledge about command filter. First, some words in the beginning. I would like to summarize one document about the command filter because what it does is really amazing. Only few software engineers seem to know about it, and many of them consider it as a module can be copied from other project, or some of them take it as a complex math-related tool. Both of the above situation may be cited because it is such a general and powerful tool for combining information in the presence of uncertainty, such as centrifugal field. Second, what command filter is. Any dynamic system which has uncertainty information can be made an educated guess about how the system is going to do in the following time step by command filter or derivation version of a command filter, such as EKF, UKF. If you could understand the basic command filters idea, it will be easy to learn other derivation version. Command filters are ideal for systems which are continuously changing. They have the advantage that they are light on memory. They don't need to keep any history other than the previous state. And they are very fast, making them very suited for real-time problem and embedded systems. The math for implementing the command filter appears pretty scarce in most places you find on websites, such as Google. That's a bad state of affairs because the command filter is actually super simple and easy to understand if you look at it in the right way. Thus, it makes a great article topic, and I will try to explain it with lots of clear, pretty pictures and colors you can find from my GitHub. The previously are very simple. All you need is basic understanding of probability and matrices. I will start with a loose example of the kind of command filter can solve. 3. What can we do using command filter? Let's make a toy example. You are build a little robot that can wander around in the woods, and the robot needs to know exactly where it is so that it can navigate. I will say our robot has a state xk, which is just a position and a velocity. Xk, note that the state is just a list of numbers about the underlying configuration of your system. It could be anything. In our system, its position and velocity, but it could be data about the amount of fluid in a tank, the temperature of a car engine, the position of a user's finger on a touchpad, or any number of things you need to keep track of. Our robot also has a GPS sensor, which is accurate to about 10 meters, which is good, but it needs to know its location more precisely than 10 meters. There are lots of gullies and cliffs in these woods, and if the robot is wrong by more than a few feet, it would fall off a cliff. So GPS by itself is not good enough. We might also know something about how the robot moves It knows the commands sent to the wheel motor, and it knows that if it's headed in one direction and nothing interferes, at the next instance, it will likely be further along that same direction. But of course, it doesn't know everything about its motion. It might be buffeted by the wind. The wheel might be slip a little bit or roll over bumpy terrain. So the amount of the wheels have turned might not exactly represent how far the robot has actually traveled, and the prediction won't be perfect. The GPS sensor tells us something about the state, but only indirectly, and with some uncertainty or inaccuracy. Our prediction tells us something about how the robot is moving, but only indirectly, and with some uncertainty or inaccuracy. But if we use all the information available to us, can we get a better answer than other estimate would give us by itself? Of course, the answer is yes. And that's what a common filter is for. And the next part is how common filters see our problems. Let us look at the landscape we are trying to interpret. We will continue with the simple state, having only position and velocity. We don't know what the actual position and velocity are. There are a whole range of possible combination of position and velocity that might be true, but some of them are more likely than others. The common filter assumes that both position and velocity are random and Gauss distributed. Each variable has a mean value called mu, which is the center of random distribution, and its most likely state. And another variance is psi, which is the uncertainty. In the above picture, position and velocity are uncorrelated, which means that the state of one variable tells you nothing about what the other might be. The example below shows something more interesting. Position and velocity are correlated. The likelihood of observing a particular position depends on what velocity you have. This kind of situation might arise if, for example, you are estimating a new position based on an old one. If our velocity was high, we probably move farther, so our position will be more distant. If we are moving slowly, we didn't get as far. This kind of relationship is really important to keep track of, because it gives us more information. More measurements tell us something about what the other could be. And that's the goal of the common filter. We want to squeeze as much information from our uncertainty measurements as we possibly can. This correlation is captured by something called a covariance matrix. In short, each element of the matrix is the degree of correlation between the I states variable and the J states variable. Covariance matrices are often labeled as this label, so we called the element I and G